All right, let's see what this page in your notes is all about. This is your unit circle. I'd be careful with this. This will come in handy for a long time. So first thing that we're going to take a look at, we've got copies of our special right triangles up here at the top, right angles right here. We know that this is the 45, 45, 90, but we know now that we can refer to that as a pi over 4, pi over 4, pi over 2 right triangle. And this one as a 30, 60, 90, this one would be a pi over 6. This is pi over 3. Let's see if I can zoom in a little bit farther on that. Get those to show up better. Pi over 6, pi over 3, and of course pi over 2 in the corner down here. Now, in the last video, we looked at how we could draw the terminal side of an angle on the unit circle because our angles of rotation were centered at the origin and initial side was on the positive x-axis, and then we were able to use sine and cosine to figure out what the coordinates of the points were. Now we're going to kind of reverse that a little bit and take a look at some of these points that I have marked around the triangle here. So I have copies of my 30, 60, 90 triangle. So here's my pi over 6, pi over 3, pi over 2 right triangle. I guess before we jump too far into that, we should put our ratios on there. If we make a hypotenuse 1 in each case, and we know the short side over here is a half, and the longer leg is square root of 3 times a half, which is the square root of 3 over 2. Over here, these both would be the square root of 2 over 2 in there. So that is the numbers that I have on this triangle right here, and we can see that what that means is that if we drew an angle of rotation of pi over 6 radians, it would hit this point out here, and the coordinates of that point would be equal to root 3 over 2 comma 1/2. So we know the exact location of that point. Okay, and that point again was created because we had an angle of rotation of pi over 6 radians, and that's where the terminal side intersected out there. Okay, to the inside here, I'm going to mention that this is pi over 6, or also known as 30 degrees. If I brought my other one in here, I'm going to bring my 45, 45, 90 in here. Okay. Got to kind of read the thing sideways there a little bit, but with the 45, 45, 90 in there, that means that this point out here, its x-coordinate will be the length of this side of my 45, 45, 90, which is the square root of 2 over 2. And since it's an isosceles triangle, the y-coordinate will also be the square root of 2 over 2. Okay. And that again was for an angle of pi over 4 radians, which is equivalent to 45 degrees. And my other one, I can grab my 30, 60, 90 triangle here again and look at what the 60 degree angle, or the pi over 3 radian angle down here. Let me kind of color that side in a little bit so it's a little more visible. That should help a little bit. So we can see where that goes up there, and so the x-coordinate, the distance along the x-axis, is 1/2, and the distance along the y is going to be up square root of 3 over 2. Okay, this uses the same circle, so it's not unusual, shouldn't be surprising that it has the same numbers involved in it that the pi over 6 radian angle had as well. Now, some points that we don't even need the triangles for. This is the point 1, 0. This is the point 0, 1. Okay. Now, up until this point, we haven't done a lot of talking about how, talking about values of sine and cosine and tangent for angles that were not acute angles in a triangle. Okay? But the same process that we did over here, we could also talk about, and this ties to the other video, that if we were trying to find the length of this side and we knew the hypotenuse was 1, then this says that this is the opposite side, so the sine of pi over 6 is 1/2 over 1. So this coordinate, this second coordinate here, also happens to be the sine of the angle of rotation whose terminal side hits that point. And this is true every place around this circle. The y-coordinate is always the sine of the angle of rotation with the terminal side that hits that point. So we can make note in here, we'll try to find some place clean to do this, that the points on this are always the cosine of the angle, comma, the sine of the angle. Okay? That's an important thing to remember. It tells me that the cosine of 0, because this is 0 degrees, it's 0 radians, it's also 2 pi radians, it's 360 degrees. The cosine of 2 pi is 1, the cosine of 0 is 1, the sine of 0 is 0, and the sine of 2 pi is 0. Okay? This up here, angle-wise, we didn't write our angles in up on this one. This was our pi over 3 radians, which is equivalent to 60 degrees. And this then is equivalent to 90 degrees. That's pi over 2 radians, or 90 degrees up there. And we can say that the cosine of pi over 2 is 0, and the sine of pi over 2 is 1. Okay. Now there's a bunch of symmetry that comes into play. Okay. It may take a little while even to find the angles on this, but we could certainly write the coordinates of this point. Okay. That comes from this 30, 60, 90 triangle again, and it has the same y-coordinate as this point, and it has the same x-coordinate except that it's on the negative side because it's in the second quadrant. Okay? So this point clearly should have the coordinates of negative 1/2, comma, square root of 3 over 2. You need to maybe pause and think long enough that you understand completely why that's what that has to be. Okay? Let me bring another piece of paper in here to come straight across from this one. So if we come straight across there, okay, that shows that it has the same y-coordinate over here. So this y-coordinate should be square root of 2 over 2. And where there's a root 2 over 2, there's another root 2 over 2. But because of the quadrant that it's in, this should be negative root 2 over 2. Okay. Now, the other thing I want to show you about finding where these angles are, because I think from symmetry at this point, you ought to be able to fill out the coordinates of all the remaining points on this, and that's what you should do. You should go through and fill out the coordinates of every remaining dot on the circle. You have everything that you need to be able to do that. Now, for the angles, this jump right here, this distance is pi over 6 radians. This is 1 pi over 6. If I take an exact copy of that and do it from there, this is now 2 pi over 6s. But 2 pi over 6 reduces to pi over 3. This would be 3 pi over 6. Okay, but 3 pi over 6 reduces to pi over 2. 3/6 is a half. If I take that same size jump again over here, this is now at 4 pi over 6. But 4 pi over 6, 4/6 is 2/3, so this must be 2 pi over 3. There's the 2/3, and that's equivalent to adding 30 degrees every time that I did that. If I add 30 degrees onto 90 degrees, I get to 120 degrees right there. These equivalences, a bunch of them are also on the last page of notes. So I can jump by this size. I can jump by pi over 6s and just count them. This is 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6, 12 pi over 6, 12/6 of course is 2, that reduces to a 2 pi. If I jump by a quarter of a circle, or this is actually an eighth of the whole circle, this is pi over 4, so that's 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4, 8/4 is 2, takes me back to the 2 pi. I can also jump by what this is, pi over 3. This gap, this distance around here, that's 1 pi over 3. This would be 2 pi over 3. This is 3 pi over 3. 3/3 is 1. This angle is pi radians, or 180 degrees. That was 3 pi over 3. This is 4 pi over 3, right there. That's 5 pi over 3, 6 pi over 3, 6/3 is 2. That's the 2 pi. I could even go by pi over 2s. This is 1 pi over 2. This is 2 pi over 2. 2 halves is 1. There's the pi. This makes that 3 pi over 2. I don't know that one yet. 3 pi over 2, which is the same as 270 degrees. And 4 pi over 2, and 4 over 2 is 2. Takes me back to the 2 pi. Okay. That should be enough information for you to fill out the rest of that. And when you have that all filled out, that means you know exact values for the cosine of the angle and the sine of the angle. And remember, tangent is the opposite over the adjacent. So if I was doing this, my opposite side here is 1/2. My adjacent side is root 3 over 2. So it would be 1/2 over root 3 over 2, which is the sine divided by the cosine. So that's information that we also now have, is that if I want the tangent of the angle, that's equal to the sine of the angle divided by the cosine of the angle. So I can do 1/2 divided by square root of 3 over 2. Incidentally, when I look at that, that is also the rise over run of the terminal side of this angle. Okay? So this is also equivalent to the slope of the terminal side. I'll write this fairly small so I don't clutter up the area that you might need for writing your angles on the inside. So we can do those divisions. Remember, dividing with fractions, you multiply by the reciprocal, and you will find common numbers showing up for the tangents as we go around there as well. So this will furnish us with exact values for the sine, the cosine, and the tangent for every angle that's associated with any of the special right triangles all the way around the unit circle, no matter how many times the angle of rotation might take me around. Okay. That is where I'm going to stop that one.